Okay. We went over this roughly, but this is the basics of what happens when there's an abrupt change of cross-section, okay? In trying to develop this equation again, as plane waves go from one duct or pipe into another one that has a different cross-section, of course, in an area that's just around the intersection, there will be unusual wave shapes, waveforms that will develop. So we assume, we make some assumptions that the distortions that are caused, geometric distortions that are caused by this, both in terms of reflection and in terms of propagation, transmission, decay very quickly, okay? In other words, the distortions around here don't propagate all the way, so we neglect them. Basically, for distances larger than a wavelength, we're ignoring them. By saying that, then, we say pressure just before and pressure just after, where they intersect, will be equal to each other. Because if they're not equal, what happens? Then you have to have very large accelerations, and that is also not true and not realistic. Now, the next boundary condition, as we did before, the conservation of mass must be satisfied. Okay, so the flow that goes to the dotted line on one side and the flow that continues on the other side must be equal to each other. This is where the abrupt change of cross-sectional area comes into play. So for wavelengths larger than epsilon, that essentially, do you need something here? Okay. Yeah. Okay, so what we will do now is we just simplify these boundary conditions with an approximation saying that pressure will be equal at the boundary from both sides and particle velocity times the area will be equal. So I'm going to rewrite these in a simpler form for use. Okay, so these are the boundary conditions. The next thing we do, what we have done always, okay, in terms of those infinite media sound propagation from one medium to the next, we have always written incident pressure, reflected pressure, and transmitted pressure. So we write the pressure field by summing the incident and reflected here and the transmitted, and apply the boundary conditions that are with which you're not familiar. These lines, I don't know where they're coming from, so don't pay attention to that. It's just the artifact of PowerPoint. So, sound pressure field on the left-hand side is the incident pressure going in the positive x direction and reflected pressure coming back from the intersection where it sees an impedance change and that causes the reflection. And the transmitted wave, again, has a positive. Because these are the same medium, air, water, whatever it might be, we don't change K. Now, there will be occasions, okay, that you would have a membrane here and one fluid here, one fluid there. Then these will be the same, but this will be different than those. Okay, then you need to maintain the differences and keep them in mind as you write the equation and solve the problems. Now, if you apply the boundary conditions, clearly you have at x0, we call this, just set this to equal to 0. A1 plus B1 will be equal to A2. But in the particle velocity, we're going to now get the cross-sectional areas involved. If we divide these, okay, if you divide them, number one, did I miss something? No. The reflection coefficient will be a ratio of the differences in the area to their sum, and transmission coefficient will be 2s1 divided by the sum of the areas. Now, do you see anything familiar here? Think about it.
It's like psi values.
Exactly. It's like zeta, right? And then zeta, yes. Well, I mean, it doesn't matter. We use different expressions. What was zeta? It was the ratio of the specific acoustic impedances. Okay? So in this case, what would it be? It would be S2 over S1. What does that tell you? It tells you, again, reflection coefficient, transmission coefficient depend on the impedance change. Okay? Whether the impedance change is due to density times the specific acoustic impedance, or the impedance is due to area change only. Okay? But if you had both the media on both sides changing as well as the area, then they would both come into play. Okay? So that's a pattern that one needs to remember. Now, let's do a quick example here. Let's say terminal area is 1/2 of the tube area, okay? So you have sound field coming here, S1, and this is S1 over 2. It's instructive to go through this and see how much sound energy is changed because of that. Okay. First, the reflected wave, if we put it down, the amplitude of the reflected wave is 1/3 of the incident wave. Okay. Just simply, we use the previous equation, S1 minus S2, S1 plus S2, and the result is 1/3 the amplitude is reflected back when the area is 1/2. Transmitted amplitude, we substitute again in the appropriate values. Now, this is interesting. Okay. 4/3 the incident amplitude is the pressure transmission. Does that make sense? Well, yes? No? Maybe?
We were discussing about this yesterday.
Oh, you were. Okay. What did you come to? What's your conclusion?
I think it's possible because the pressure change accompanies to velocity change and conversation about the energy. So.
Okay. So this is perfectly fine. What would not be fine is more energy being transmitted. This is not energy, this is pressure. Okay? So that's perfectly okay, if you have done it right. So let's look at the energy that's transmitted here. Okay? Energy densities are proportional to the square of the amplitudes. So incident energy minus reflected energy is equal to the transmitted energy. And if you put it all together, you see that only 1/9 of the energy is reflected. Remember, it was 1/3 the amplitude, but only 1/9 that's reflected. In all of these, what you need to keep in mind is the energy conservation. We do not have, in these examples that we have done, a loss mechanism. So energy is not lost. You would have energy loss if there's an absorption, which we will get to later on. Okay, if there's an energy absorption, the sound waves are absorbed, much like vibration damping, absorbed and converted essentially to heat. Okay, that you need to calculate separately to make sure the conservation equation is satisfied. But in these transmission problems without any absorption, you need to be able to account for the conservation of mass. And let me define what we mean by transmission loss. Okay, transmission loss is a very particular definition. Incident power divided by transmitted power log multiplied by 10. Okay, that's the transmission loss. And this is a definition that applies to just about everything. And I'll explain what I mean by that. When you speak or specify, let's say, construction of a wall, okay, you would say, I need to have this wall to have a transmission loss of such and such at certain frequencies, okay? And this is how you would calculate it. But see, transmission loss has to be dependent on frequency. We probably will start talking about this next week when we start studying plates, okay, vibrational plates, how they radiate and how sound is transmitted. It depends on the frequency. So you would calculate the transmission loss at certain frequency regimes, and then there's a way to add them to give you certain values. So this is the definition of transmission loss. And because it says power, okay, and because power is area times an intensity like quantity, intensity is pressure squared for plane waves, divided by the specific acoustic impedance, but this is the same fluid, so we use the same one. If it were going from one fluid to the next, you would have to keep these in here, okay, divide them. You remember this? We did this last time. Power is intensity times area. And intensity for plane waves can be expressed as square of its amplitude of the pressure divided by specific acoustic impedance. Because it is the same fluid on both sides, we have not included here, but it is smart to keep these in mind, okay? Because if you just blindly use the equations, then you could make a mistake. And because we have from earlier the expression for the ratio in terms of the areas, the transmission loss can be expressed as you can see, purely in terms of the area difference between the two. Now, what is important here? This was derived for sound wave coming from one side going to the other and some of it being reflected. You see this figure is slightly different than the one I showed you before. It was the other way around, okay? If you look at this equation, this has no directionality. So it's true. Doesn't matter which side it comes from. As long as there's a change, all you need to know is the area signs, but not the direction. It's an impedance change. That's all the sound field cares about. Okay? Transmission loss is symmetric with respect to its direction. What do we do with this? What can we do with this concept? Well, we can make silencers, okay? Exhaust mufflers or any other kind of silencer that to use to attenuate sound waves that are propagating in a duct. The example that we'll have here is you have a duct. Let me just clear this. You have a duct through which sound field is propagated. Now this could be a heating, air conditioning type of duct, or it could be a water carrying pipe, some sort of hydraulic system, and pressure waves are headed and they are delivered to parts of either a home, structure, ship, whatever it might be, automobile, okay? That you want to suppress this. You want to make this less. So what we want to do then is we cut a part of it and insert what we call a silencer. It's just an expansion chamber. Now, this is very simplistic. The expansion chambers have become much more sophisticated now. Inside are membranes filled with liquid to even do more to attenuate the sound field. But let's just see what happens if you only change the cross-section at one spot in the pipe. Let's see what we can do. What is it that we're after when you look at something like this? You are an acoustics engineer, okay? They say, find out how to design a silencer like this. In fact, there's a problem here. They need a silencer in one of the buildings. How do you design it? Well, you say, what does that mean? What that means is, what do I want? In terms of what you have learned. What is it that you want? The last topic we covered, go ahead.
I want for silencer.
Yes.
To attenuate the pressure of the sound.
Exactly. Transmission loss is something we just talked about. What you want to do is you want to increase the transmission loss, right? The more the loss, the less the sound here is. So how do I find out what is that transmission loss? Well, sound field comes from the left-hand side. There's an impedance change. It propagates. There's another impedance change. So I want to find out what the transmitted sound pressure here is in terms of incident sound pressure here. Okay? But to be able to do that, I also need to deal with this because this is the one that pulls two sides together. So the first thing I do then is, in words, I'll write these down, get the sound pressure incident, it will reflect. Then that will continue, but then reflect again, and then some of that will continue down. That's the transmitter. So what we'll do is write the acoustic field for each section and then eliminate the central part and determine the ratio of transmitted to incident wave. Okay? I'll pull these down slowly so you can write them. Okay? So the field on the left-hand side is incident plus reflected. You should be able to write these without even looking at the board quickly. Okay? Yeah, this is becoming familiar. I'm emphasizing these over and over because this should be a second nature to you. And we will go on to spherical coordinates. It's identical conceptually, and you'll be able to do them well. Okay, so that's the pressure field on the left-hand side, incident and reflected. Inside the silencer, or the cavity, we have, once again, an incident and reflected wave. Just different amplitudes. We don't know what these amplitudes are yet. And finally, we have a transmitted wave. Boundary conditions. What are the boundary conditions on these? There are two types of boundary conditions. One will say, as we just discussed a moment ago, pressure will be the same. Pressure will be the same. But when it comes to particle velocity, S1 times U1 and S2 times U2. Similarly, S2 U2 and S1 U3. Okay? And if you apply those, and I'm just jumping through these, if you apply them at x0 for the particle velocity, that gives you the upper. Let's see. I'm making notes to change things as we go along. Okay. Particle velocity gives you the upper one, and pressure gives you the second one. Now we're going to x equals L. Particle velocity written in terms of pressure transmitted, and also particle velocity inside the chamber. And similarly, pressure transmitted and pressure inside the chamber. You'll see now this brings a new term or a new expression that you haven't seen very frequently before. K times L. Okay? L is the length of the silencer. And K, of course, KL, K, of course, is the wave number, which is ratio of frequency. And let me just go further, 2 pi over lambda. This is also K. And if I write it, now, you see an interesting non-dimensional value, length versus wavelength. This is going to be important as we go along further on this, okay? So the reflection coefficient can be written, pulled out of these. What is the reflection coefficient? PR over PI. Reflection coefficient has basically 2 parameters. What are they? What are the 2 parameters? Area ratio and KL. Okay? Now, if you take a look at this, reflection, you can make reflection 0. Absolutely no reflection if you set KL to be equal to odd multiples of pi over 2. Sorry, pi. Multiples of pi. No. Well, what that suggests is I can select this length such that it behaves as if it's not there. That's what it says. Everything is just gone through. It's transparent. But for that frequency only. Okay? For that frequency only. So some frequencies will just shoot straight through. Okay, very interesting. This is worthwhile to keep in mind. The other thing is these ratios. We'll have some problems, homework problems, exercises to examine the value of these and what they mean. This is very small. And the second expression is transmission coefficient. These are pressure, okay? Pressure reflection and pressure transmission expressions. You can go home and demonstrate to your satisfaction that absolute value squared of reflection and transmission coefficients add up to 1. Why is that? Conservation of energy. We don't worry about area because both the reflected part and the transmitted part has the same area. Okay? And so energy is conserved. Make sure that you're able to demonstrate square of this absolute value and absolute square of this add up to 1. I would encourage you to do that. I think it's a wise thing to do. Now, the transmission loss, if you go back here, this is pressure transmission coefficient, and the transmission loss is defined as 1 over t squared, absolute value. Okay? Our purpose is to make the transmission loss maximum, right? Send all the sound back. When you have a quick look at this, for a given area ratio, what makes the transmission loss maximum? Quickly. What makes this value maximum? We want to say again?
Bigger 8.
Well, maybe. But it also makes this small. Say again?
Selecting KL is equal to 90 degree.
KL must be pi over 2's multiples, right? Odd multiples. So if this is 1, then it's 1 plus. If this is 0, then you have log of 1, which is 0. Remember, if this is 0, we already said it goes straight through. Transmission loss is 0. Okay? So these are some numbers that you can keep in mind. There's also an optimum value for the ratio that you can look at. So let me see if I have.
The length of the silencer is much more important than the area.
I don't know that it's much more important because there are, how shall I put it? I wouldn't say that it's much more important. There are two different things that go on here. Number one, this is valid for a particular frequency, okay? Whereas this is in general terms. And there's also the practicality too. Yeah. So the maximum transmission loss is maximum whenever that sine KL is plus or minus 1. And it's 0 when obviously it is equal to 0. So the one thing to keep in mind is the geometry of this. Okay, the geometry of the silencer is not that important. You're not looking. The geometry of the silencer is not important. It could be any kind of volume as long as its area change occurs in a distance that's less than lambda. Meaning, you do not want to have a change like this, where this change is comparable to the wavelength. Then it's not going to work. Okay? You want it to be an abrupt change. So there's an impedance change, not like a horn speaker. What is this last statement? At high frequencies, they're not as effective. Why is that? Go ahead.
We can't make realization.
That's right. At high frequencies, the wavelength is much shorter. Higher the frequency, shorter the wavelength, and then we're not able to make that area change in a distance that's smaller than the wavelength. That's why it doesn't see the impedance and it goes straight through. Just to put some shapes on these. The maximum transmission loss shows us these dotted lines describe the amplitude of the pressure. Okay, we select the length such that at that frequency, if it corresponds to 1/4 the wavelength, or 3/4 or 5/4, then it is such that the pressure at the other end is at a nodal point, 0. That's what this means. Okay, when that's the case, then sound pressure just does not propagate effectively in the other direction. Okay, any questions on this? On the silencer? The one thing that you should do is obtain these. It's just simple algebra, mathematical relations. But I would urge you just to go ahead and obtain these. The rest, I think you know what to do, okay? Even if I hadn't done this in class, you would be able to do that. Okay. Acoustic transformer, okay? Once again, it's the concept of changing a cross-section. Just like what we have done before. We said we have two boundary conditions, P1, P2, and conservation, area times particle velocity, area times particle velocity. Well, when you do that, okay, if one area is larger than the other one, then essentially you are amplifying the particle velocity. Remember earlier we had a large amplitude for the pressure transmitted, okay? It's an amplifier. See, particle velocity is now changed as a ratio of the areas. This is called an acoustic transformer, and it's usually used, the concept is usually used for horn speakers as follows. There's a membrane that vibrates, and in front of that membrane is a volume like this. So as it goes from this cross-section into this, it amplifies the particle velocity, the tiny one, to a large value. That's one example of how you use an acoustic transformer, okay, to get larger flow of particle velocity into the system. So in this case, purely by the ratio of the areas. Now, for example, without that ratio, the horn speaker would generate a sound power that's expressed as S1 times the radiation impedance U1 square over 2, okay, where R is the radiation impedance times the cross-sectional area of the horn opening. I'm going to go over this very quickly, but just to demonstrate what the difference is. I will rewrite this in the next one, I think. Well, you can already see the relationship of how sound power is proportional to the radiation area. But okay, radiation resistance. This is the radiating part of the impedance. But coming back, I'm rewriting the sound power radiated without that amplification. With the amplification, now you can see the ratio is much different. This is cross-sectional area, radiation resistance, and once again, U squared over 2, which is proportional to the impedance. And what we now see is that the effective radiation resistance is proportional to the areas. This is really what I want to show to you, how the acoustic power is amplified purely as a result of change in cross-sectional area between the front of the horn, front of the acoustic membrane that's radiating, and the horn itself. Any questions on this? No questions? Okay. Let's see now. I'm trying to judge the time. Okay, let's push forward. Helmholtz resonator. We did a short derivation of Helmholtz resonator probably in the first week. And just to remind you, an example of a Helmholtz resonator is when you have a small bottle and then you blow in front of it, and that makes some sort of a sound. It's generating sound. That's called a Helmholtz resonator. And we can model the Helmholtz resonator as some sort of a volume, a cavity, okay, which has a neck. It doesn't have to, but it has a neck. And that's called the length of the neck as L, cross-sectional area S. We have a pressure on the outside and pressure on the inside, and there's some sort of oscillation, okay? Now, as you blow onto it, or wind goes through it, mass flows in. If the mass flows in, density must rise. This is another example of this is cars. When you're driving on the highway, if you open the window of the car just a little bit, okay, that acts like this opening here, and then you can actually feel this resonance. That's a Helmholtz resonator, same concept. Or sometimes a small pinhole, then you can hear the whistling, okay? So what we have here is to demonstrate the rise of the density, change in density times velocity as the mass flow. So for harmonic change, e to the I omega t, we can express the density change in terms of mass flow into the system. Okay. Now, that density change in terms of mass flow Okay? Density change, of course, gives rise to a fluctuation in pressure inside the volume. Okay? Speed of sound, C, and density change. Once again, mass flow changes the density fluctuation. We can express it in terms of density fluctuation, and which gives rise to pressure fluctuation. Okay? Just the neck part now. We want to have a momentum balance. The acceleration of the mass in the neck. Okay? Right here, it oscillates back and forth as a result of the pressure difference on either side of it, okay, inside and outside. Now, yes. We have the expression for pressure here. We substituted back here, and did I miss something? Okay. Substituting for the pressure, now we have an expression for P1 in terms of mass flow, cross-sectional area, length of the neck, volume of the cavity, and the frequency of oscillations. The expression here, C square S divided by VL, you can consider that as a resonant frequency. And near that value, very little change in pressure will give very high, large mass. Oops. Variations. Okay, so the system resonates at this frequency. And small variations of pressure gives large variations to mass fluctuations. Here's a Coke bottle example. Coca-Cola. Okay, its volume is. Let me see, what is the value here? 5 times 10 to the minus 4 meter cube. Cross-sectional area of the opening is 2 times 10 to the minus 4 meters squared. Length of the neck is roughly 5 centimeters. So if you calculate all of this, you'll have a resonant frequency about 1,000 radians per second, or about 150 hertz. And that is actually very close to what you hear when you blow on a Coke or a beer bottle. Yeah. Okay. Let's take a 3-4 minute break, and then we'll come back and see what we can do with a Helmholtz resonator. Okay?